Hi, I'm Professor Melko, Chemistry PhD, and today we're going to talk about Dmitri Mendeleev and the periodic table, and learn some of the history and vocabulary that goes along with the periodic table and how chemists use it today. So let's jump into the lecture. So this is the guy, the man, the myth, the legend, Dmitri Mendeleev. He was really the first one to propose organizing elements by their properties. Okay, and he first did this messing around with playing cards. So he would write on the back of playing cards the properties of the various elements, and then he would go through and sort of lay those elements out in groups. Okay, and he noticed that when he organized these elements based on their properties, he sort of had this organizational table setting itself up. Of course, he arranged elements by increasing mass, and we'll see it's better to do it in increasing atomic number or number of protons. But he didn't have a lot of that information at the time. He was doing it in order of increasing mass, and we really had to wait until we knew what protons were and how many protons each of these things had to correct on his initial table. But that's the first periodic table organizing these elements by mass. Now, the real revolutionary idea that he had was once organizing these things into a table, there were blank spots in the table. So if I go back a slide real quick, you'll notice there's some things missing, right? Where there should be playing cards, there are no playing cards. And so this organizational schema, this table, allowed him to predict that elements actually existed with those properties in those spots. And that's the story of germanium, which he called eka-silicon. So he knew about silicon, knew about its properties, knew there should be something like silicon that had a higher atomic weight. And so he made these predictions, all of these numbers here, and 17 years later, this element that is like silicon was discovered and named germanium. And so that's really when Mendeleev got a lot of credit and became famous, is that he was making predictions that turned out to be true. And this happens a lot in science and chemistry. You have this hypothesis, you might elevate that to a strong scientific theory, and then you make predictions based on that theory. And if they turn out to be true, that further reinforces your scientific theory. If it turns out the experiment proves it false, then we sort of go back to the drawing board and ask more questions. So Mendeleev correctly predicted this new element that was discovered 17 years later. And he made other similar predictions. Now, turns out organizing these elements by atomic mass is not quite correct. You want to do it by increasing atomic number. And this was done by Moseley, who doesn't get nearly enough credit, but he was the one that sort of took these cards laid out in a table and slightly reshuffled them, organizing them by atomic number. When you do this, it really then locks in all these patterns of chemical reactivity and other properties that are useful to chemists. So instead of just the total mass, it's just the total number of protons. And so the periodic table today is organized in this fashion, increasing atomic number. And once we organized it in this way, we sort of saw that the elements fell into these sub-level groupings. And you'll remember from the previous lecture when we talked about levels and sublevels, right? After Bohr made his model of the atom and predicted these energy levels, and after that we discovered sublevels, we knew this sort of ordering of the levels was how it went in terms of energy. When the periodic table was reorganized in terms of atomic number, these sublevels more or less dropped out, right? So this first area of elements in the table is the S block. This middle area is the D block. This area on the right is the P block. And as we move left to right through the periodic table, this element here, helium, can also be sort of thought to live right here. The first two elements are two S elements. After that, we get to a second pair of S elements. After that, moving through the periodic table, we get to a set of P elements. After that, we get to another set of S elements, then P, then S, then D. And so the periodic table really mimics this ordering of sublevels we already knew about in its structure. Now, some vocabulary that we need to be comfortable with using when we read information in chemistry texts about the periodic table. They're going to refer to things as periods or series or families or groups. And so let's just go over what each of these terms means. There are 7 periods in the periodic table. Right? So name the periodic table because these properties are periodic, they're repeating. And the periods here are what the rows are. So moving left to right, this first row here, or first period, is also known as the first series. This third period goes from sodium all the way to argon. That's everything in the third period or third series. Okay, so these two things are used interchangeably. The rows are periods or series. Now, the columns are known as groups or families. And this is where the chemical properties are similar. So anything within a group or a column are going to have similar chemical properties. So these are groups, also called families. Those are the columns. Okay, so everything from beryllium down to radium is in the same group or family. They have similar properties. Particularly that column is known as the alkaline earth metals. In all, there's 18 groups, so you can count up the columns left to right. There's 18 of them. Counting top to bottom of the rows, there's 7 of them. So 7 periods, 18 groups. Period 1, we can just count up, has 2 elements. 1, 2. Period 2 has 8 elements, right? 3 through 10. Period 3 has 8 elements, 11 through 18. Period 4 has 18 elements, element 19 through 36, and so on and so forth. You can see as I go down the periodic table, the periods or the rows get longer and longer. And this has something to do, of course, with the energy levels and sublevels. These floating elements at the bottom, the lanthanides and the actinides, right, are kind of, off on their own, pictorially here in the periodic table. But that's not actually accurate. If you wanted to think about a more correct periodic table, you would have them sort of in line here, right next to lanthanum and actinum, right? It's just shown in this separated form because it's a lot harder to visualize this periodic table in something like this. But this is strictly more correct, right? The periodic table would look something like this. Of course, it's really hard to show this on a website or a book page. So typically we get these elements and just move them down here, right? Everything's a little bit more compact, but that's why they're floating there at the bottom. It's not that they're not interesting or not as cool as the other elements. It's just for reasons of visualizing this periodic table. And you can go around online and look at different versions of the periodic table. There's circular ones, there's long ones like this, there's all kinds. There's 3-dimensional periodic tables. This is the main one that I usually show and stick to. One other thing about the periodic table I want to point out is hydrogen. It's usually shown over here on the left, right? And it sort of has some properties like the other members of its group, lithium, sodium, potassium, etc. But it is pretty special, okay? It has properties similar to these metals in some respect, but it's actually a non-metal and has properties like some of the elements over here. Okay, for this reason, sometimes you'll see this hydrogen just written in the center of the periodic table, sort of floating, and sometimes it's going to be organized on the left. So it kind of depends on the periodic table. Just know that hydrogen is sort of unique. It might be positioned on the left side of the periodic table, but it actually has a lot of properties like the things in the elements on the right side of the periodic table. Now, some other organizations within the periodic table, right? This encodes a lot of information for chemists. And so there's a lot of different terminologies. We've discussed these rows as periods and these columns as groups, but we can really break this down a little bit further. Okay, so in these groups, these different columns of elements, we have 2 separate groups. We have group A and group B. Okay, and group B here should be in red. Group B here are the transition elements, everything within this sort of central block of 10 element wide is group B. Group A consists of these first two and these last 6 groups and families. Okay, so that's how we divide up the periodic table into group A and group B. Group A is sometimes called the representative elements or main group, and group B are the transition elements. And notice neither of these groups had these lanthanides and actinides down here at the bottom. Those are kind of kept separately, of course for pictorial reasons, but they're not really falling into group A or B. We usually call these down here the inner transition elements. It's just like it sounds, these are sort of inside group B, the transition metals. Sometimes we'll also call them rare earths, because it turns out these elements in particular come in very, very small amounts in the earth. So they're hard to find, they're pretty rare. We call them rare earths. So with all this new vocabulary, let's try to assign these various elements to these groups we just talked about. So pause the video, take 30 seconds or so and try to answer this, and then I'll work it out. First thing to do is identify where the element lives. Carbon, symbol C, that's right here. This is a main group element. Okay, remember anything in the S block or P block is a main group element. Cesium, abbreviated CS, down here, that is also a main group element. Lastly, osmium, symbol OS, is right here in the middle. This is group B, or transition elements. Okay, so that's the answer to this one. Main group for carbon and cesium, and then osmium is a transition metal. If I asked for something like, let's see, plutonium, that would have been an inner transition element. Something down here in these last two rows at the very, very bottom, set aside from the rest of the periodic table. Okay, now instead of just dividing this thing up into groups, we also sometimes just number the columns. Okay, so going from left to right, you'll see these numbered designations 1, 2, 3, 4, 5, all the way up to 16, 17, 18. Sometimes we number these groups or families 1 through 18. Okay, it just depends on the periodic table, who's using it and who made it, whether it's 1 through 18 or group A, group B. Additionally, you can sometimes see group A and B written with Roman numerals. So you might see Roman numeral 1A, okay, Roman numeral 2A. And that would correspond to these first two groups or families of the periodic table. They're group A, 1 and 2, the first two groups. So that's 1A and 2A. Right? Down here in group B, this one would be 3B because it's the third, 1, 2, 3, group of this group B transition area. Right? So those are also used interchangeably. You might be asked for, you know, a group 2A metal, like beryllium, or a, you know, group 17 halogen, like fluorine. Several of these groups, of course, use alternative names, further complicating things, right? It's not enough that they're just called group 1, right, or group 1A. They're also called alkali metals. Okay, so this first row, this first column, this first group or family are known as the alkali metals, but not hydrogen, because that's not a metal. So the alkali metals are lithium, sodium, potassium, rubidium, cesium, and francium. Okay, on my periodic table here, it's sort of highlighted with these colors. in purple. Group 1 are the alkali metals. Group 2 are the alkali earth metals. There's 2 other things that get a special name. Group 17 here are the halogens, right, in red. Fluorine, chlorine, bromine, iodine, astatine. And lastly, the very last group here are noble gases. Helium, neon, argon, krypton, xenon, radon. Right, so this group 18 is noble gases, group 17 is halogens, group 1 alkali metals, group 2 alkali earths, or sometimes alkaline earth. So the alkaline earths are beryllium all the way down to radium. So let's try a practice problem here. Try to pause the video and predict what element is in the 4th period with properties like oxygen. Oxygen, symbol O, is found right here. If it has properties like oxygen, that means it's the same group or family. So we know it's definitely in this group or family since it has properties similar to oxygen. Things in the same group have the same properties. If it's the 4th period, I simply count the 4th row. 1, 2, 3, 4. So it has to be in this row with properties like oxygen. That would be selenium. Okay, so that's how you sort of can answer these types of questions if you get them on, say, an exam, or you're wondering, what is an element with properties like carbon? Well, go to the group of carbon. That might be silicon. Okay, that does it for this lecture. We sort of introduced the periodic table, its history, and some of the terminology. Up next, we'll get into periodic trends like atomic radii, ionization energy, and learn something about abbreviated electron configurations. As always, feel free to subscribe to my channel on YouTube for more content like this, or check out my weekly office hours on Twitch, where we discuss science news like climate change and space, and do practice problems like this one here, and review for exams. Catch you next time.